Hi, and welcome to this video on dividing decimals by whole numbers. Decimals represent part of a whole, so it may seem a little unusual to divide a part of something into different groups. If you had part of a slice of pizza because you had eaten the other part already, it would be a little weird to split the rest of that part with a couple of friends. But if you had part of a whole pizza left, say like 4 slices out of a whole pizza made of 8, that's not as weird to split with some friends. Another common way you will see division with decimals is involving money. Consider this example. Your grandma has $4.25 in coins and she wants to split the money evenly among her 5 grandkids. Let's go over the process of how to divide with decimals using this example. When dividing a decimal by a whole number, you want to set up your division just like you would for regular long division, like this. Then, we will work the problem exactly like we would with any other long division problem. The only difference being that we put a decimal point in our answer right above where it is placed in our problem, like this. Now, proceed with regular long division. You no longer need to think about that decimal. So 5 cannot go into 4 anytime, so we're going to put a 0 here and move on. 42. 5 goes into 42 8 times. 8 times 5 is 40, so we write a 40 underneath and subtract. This gives us 2. Then we bring the 5 down to get 25. 5 goes into 25 5 times, so we write a 5 up here, subtract 25, and we're left with 0. This tells us that your grandma should give 85 cents to each of her grandchildren. Let's try a few more examples. 8.275 divided by 5. First, let's set it up like a long division problem. Then, place your decimal point in the appropriate place in your quotient. And now divide as you would typically with long division. 5 goes into 8 one time, so we're going to put a 1 up here. 5 times 1 is 5. Write down the 5 and subtract. This gives us 3, and we bring down our 2. 5 goes into 32 6 times, so we're going to write a 6 up here. 5 times 6 is 30. Write down the 30 and subtract. This gives us 2, and then we're going to bring down the 7. 5 goes into 27 5 times, so we're going to write a 5 up here. 5 times 5 is 25. Subtract 25. Now we have 2, and we're going to bring this 5 down. 5 goes into 25 5 times, so we write a 5 up here. 5 times 5 is 25. Write 25 and subtract, which gives us 0. The final answer is 1.655. Here's another one for us to try. 0.432 divided by 8. First, set up your long division problem. Then, add your decimal point in the appropriate place. From there, divide as you would typically with a long division problem. .432 divided by 8 is equal to 0.054. Let's try one more together. This example will require a couple of extra steps that the last few didn't. 1.973 divided by 4. First, set it up for long division. Then, place the decimal point in the correct place and divide as you would normally. In this problem, we encounter something we haven't before, a remainder. If you recall when you first learned how to long divide, you were most likely taught to add a decimal and a 0 and then keep dividing and adding zeros until you no longer have a remainder. You can do this because 1.0 is the same as 1, which is also the same as 1.00. Adding a decimal point and zeros after it doesn't change the value of the original number because it just means adding 0 parts to the whole. With our example, you are going to do almost the same thing. However, instead of adding a decimal and a 0, you will just add a 0 and continue dividing. This is because we already have a decimal point and you can't have 2. So I'm going to add a 0 and then bring it down. 4 goes into 10 2 times. 4 times 2 is 8. So I'm going to write down 8 and subtract. That leaves us with 2. I'm going to add one more 0 and bring it down. And that gives us 20. 4 goes into 25 times. And then you subtract and get 0. After adding 2 zeros, we finally get an answer without a remainder, 0.49325. I want to do one more example, but this time try it on your own first. I'll give you the problem and then I want you to pause the video and find the answer yourself. Then, once you've got it, press play and see if it matches up with mine. 3.872 divided by 5. Ready? I'm going to start by setting up my long division problem. Then I'll add my decimal. And finally, I'll complete the long division process. After adding an extra 0 so I wasn't left with a remainder, I got 0.7744. Hi, and welcome to this video about manipulating equations. In this video, we will be discussing these 3 main concepts, seeing what each is, why we need to know it, and how we use it. Carrying out the same operation on both sides of the equation, the advantage of combining like terms, and canceling terms on opposite sides of an equation. Let's get started. Before we jump into it, let's quickly review some background information to ensure we're on the same page. Remember that an equation is a statement of equality. The equation 2x plus 4 equals 10 tells us that the expression 2x plus 4 is equivalent to the expression 10. It also tells us that there's some value of x that will make the expression 2x plus 4 actually equal 10, and therefore make the statement true, which in this case, x would be 3. 2 times 3 plus 4 equals 10. All other values of x make the statement false. For instance, if we tried to say that x equals 5, the left side of the equation would equal 14, and therefore not be equal to 10. Okay, now let's get into the first concept, carrying out the same operation on both sides of the equation. Since the two expressions on either side of the equal sign are in fact equal, we can use any operation we want on one expression as long as we do the exact same thing to the other expression. This is generally known as keeping equations balanced. It produces equivalent expressions and does not change the value of x that makes the original statement true. For example, we can subtract 7 from both sides, which would give us 2x minus 3 equals 3. The statement is still true when x equals 3. 2 times 3 minus 3 does in fact equal 3. Or we can divide all the terms on both sides by 2. So we have our original again, 2x plus 4 equals 10. And if we divide each part by 2, that gives us x plus 2 equals 5. Again, when x equals 3, the statement is true and all other values make it false. 3 plus 2 equals 5. Typically, when given an equation, we want to isolate x using addition, subtraction, multiplication, or division so we can see its value. So, even though we can manipulate an equation using any terms we want, there are certain operations in every equation that will help us reach a solution. Now that we've got that down, let's discuss our next concept, combining like terms. Combining like terms is an important equation solving step that is usually done before any actual solving begins as a way to simplify the equation. To combine like terms, add or subtract all of the terms with the same variable. For example, consider this equation. The 2 and the 3 in the second set of parentheses are like terms, so we can combine them. Doing so gives us this. 2 times x plus 3 plus 3 times x plus 5 equals negative 4. Now we can carry out the multiplications that are implied by the parentheses, distributing the outer 2 and 3 accordingly. 2 times x is 2x, plus 2 times 3 is 6, plus 3 times x is 3x, plus 3 times 5 is 15, equals -4. The 2x and 3x terms are like terms, so we can add them together to get 5x plus 6 plus 15 equals -4. Now the constants 6, 15, and -4 are also like terms, and we can combine them as well. Subtracting 6 and 15 from both sides of the equation will give us this. 5x equals -25, which simplifies further by dividing by 5 on both sides. 2x equals -5. Let's look at another example. In the equation, 2x plus 4 equals 16 minus x. We need to get the x terms on one side and the numbers on the other. We can add x and subtract 4. This will give us 3x equals 12. Or we can subtract 2x and subtract 16. So if we try this one again, we have 2x plus 4 equals 16 minus x. And if we subtract 2x from both sides and subtract 16, that will leave us with -12 equals -3x. Regardless of the steps to combine the like terms, the solution is the same. X equals 4. Divide by 3 on both sides, and we get that x equals 4. And here, divide by -3 on both sides, again gives us that x equals 4, since dividing a negative by a negative results in a positive. Now on to the third and final concept we're going to cover, canceling terms on opposite sides of an equation. Sometimes manipulating terms in an equation is called canceling or canceling out. Two terms on opposite sides of an equation can be canceled if and only if they exactly match each other. They must have the same variable raised to the same power and the same coefficient. Canceling can be done by using any of the 4 operations, but there is a more specific way to think about what we're doing. When we add or subtract a term to both sides of an equation, we're making a 0 by adding the opposite of a term. In the equation, x plus 6 equals 13. We would solve by subtracting 6 from both sides. By subtracting 6 from both sides, we made a 0 on the left side, since 6 minus 6 equals 0, allowing us to solve the equation. By the same token, in the equation x minus 5 equals -4x, we might subtract x from both sides to make a 0 and find the solution. Then we'll divide by -5 on both sides to get that x equals 1. With multiplication and division, the goal is to make a 1. In the equation 3x equals 9, we need to make that 3x into a single x by dividing both sides by 3. Since 3 over 3 equals 1, we were able to solve the equation. Thinking about manipulation in terms of making zeros and making ones will help you determine the path to finding a solution to any equation. Let's practice a couple before we go. Solve. X minus 3 over 2 equals 6. Make a 1 by multiplying both sides by 2. X minus 3 equals 12. Then make a 0 by adding 3 to both sides. X equals 15. Solve. 8x plus 7 equals -11 minus x. Make a 0 by subtracting 7 from both sides. 8x equals -18 minus x. Make another 0 by adding x to both sides. 9x equals -18. Make a 1 by dividing both sides by 9. X equals -2.
Have you ever put an ice cube in a heated skillet and watch it transform from ice to water, then to evaporate out of the pan and make steam? What you're seeing is that piece of matter changing in its state. Hey everyone, welcome to this video on the states of matter. There are three primary states that matter exists in: gas, liquid, and solid. However, in very extreme cases, matter can exist in other states, like plasma, more specifically, hot plasma. Gas. Within a gas, particles have large gaps of space, and there's no specific pattern to their arrangements. The particles move very quickly and freely. Since there's a lot of space between particles, gas is compressible. Gas can easily flow since particles dart past each other, and gas takes the shape and volume of the container that it's in, since the particles move freely. Liquid. Particles within a liquid are much closer together, but they also do not have a specific arranged pattern. These liquid particles move, but not quite like gas particles. They vibrate, slowly move about, and they can also move past each other. Because the particles can move, a liquid can fill the shape of the container it's in. However, it will not fill the whole space like gas, depending on the volume of water to volume of container ratio. Since there is not as much space between the particles, liquid is not easily compressible. Liquid can flow pretty effortlessly, which is due to the particles' ability to slide and move past each other. Solids. Now, particles within a solid are very, very close together with very little, if any, space between each other, and they are generally arranged in a specific pattern. Typically, solids do not move about, but they will vibrate in place. A solid has an already fixed volume and shape, since there is little to no major movements of the particles. A solid is also not easy to compress because of the lack of space between the particles already. Solids do not flow easily because of the lack of movement of the particles and their inability to move past each other. Now, plasma. I mentioned that this only happens in extreme cases. Plasma is extremely hot gas that is ionized. Plasma has significantly different characteristics than the other three states of matter, so it is thought of as the very distinct fourth state of matter. However, it is closest in similarity to that of a gas. Having an understanding of what's going on with the particles within matter is very important. They're not just simply tiny pieces of solid or liquid or gas, they are molecules and atoms. What is happening with those molecules and atoms, their physical characteristics, is what decides their state.
Hi, and welcome to this review of Newton's first law of motion. In this video, we'll see how it forever changed people's perception of how and why things move. Understanding how and why things move has been the goal of scientists for thousands of years. Over time, calculations and experiments helped pave the way for a deeper understanding of motion, with Galileo Galilei defining the laws of gravity in the 1580s and Johannes Kepler penning his laws of planetary motion in 1618. The basis of our current understanding of motion comes from Sir Isaac Newton's three laws of motion, which he established in 1687. In this video, we'll be discussing his first law of motion, also known as the law of inertia. Newton's first law of motion states that an object at rest will stay at rest, and an object in motion will stay in motion unless acted on by a net external force. This statement is much more intuitive than it sounds. One of the key things to remember, though, is that this law is only valid for objects in an inertial reference frame. An inertial reference frame is a frame of reference that is moving at a constant velocity. Let's think of it this way. When you kick a soccer ball and it soars through the air, the soccer ball isn't the only thing that's moving. Remember, we're on a planet that's rotating at about 1,000 miles per hour, our solar system is moving at about 140 miles per second, and our galaxy is rotating at 130 miles per second. So objects that we consider to be stationary on Earth are technically moving at a speed of almost 1 million miles per hour. However, it's generally pointless to include the motion of things like the solar system and Earth when we talk about the motion of things on Earth, like cars or people. What we do instead is use Earth as a point of reference, or an inertial reference frame. That is, we discuss the motion of objects in reference to Earth. Let's take a look at an object in an inertial reference frame that has a velocity of 0. It would seem that there are no net external forces acting on the car since the car isn't moving. But what about gravity? Isn't that an external force? While it's true that gravity is pulling the car downward toward Earth, the car is on the ground, and the ground is providing a force in opposition to gravity. This force is called the normal force. Since you have two equal forces acting in opposite directions, the forces cancel out, meaning that the car does not move in the vertical direction. We define force by the symbol F, noting the force is a vector, which means it has both magnitude and direction. By doing this, we can state Newton's first law, mathematically, as the sum of the external forces is equal to the upward force of the ground on the car minus the downward force of gravity on the car, which is equal to 0. Note that the negative sign in front of the force of gravity indicates the downward direction of the force of gravity. This implies that the upward force is equal to the downward force. Now, let's imagine that someone comes along and pushes the car for a moment, providing an external force and giving it a small velocity. According to Newton's first law, once the external force is removed, the car should continue to move in a straight line with a constant speed for the rest of eternity unless some other external forces come along and change its speed or direction. Mathematically, we could state that the change in velocity with respect to time is 0. What we've just described is the constant motion of an object that is in a frame of reference with 0 velocity. However, what if we made the car the inertial frame of reference and discussed the motion of the passengers inside it? Imagine if you and I were sitting in that car and there were no other objects around. In that frame of reference, you and I are not moving with respect to each other. We are both moving in the same inertial frame. If the car changed speed or direction, you would feel it because your body wants to keep moving in the straight line with constant speed. If we look at the head as an object moving in the inertial frame of reference of the car, if the car sped up, your head would feel like it's being thrown backwards. This is because the part of your body that is attached to the car would speed up too, but your head wants to obey the law of inertia and continue moving at a constant velocity, that is, with the same speed and direction. Similarly, if the car were to turn to the left or the right, your head, due to inertia, would feel like it was being moved to the right or left. Let's look at another simple example in which you are trying to push a piano across the stage for your performance at your high school graduation. We have already discussed what the forces should be in the vertical direction, where gravity is pulling the piano down and the stage is pushing back up, so there is no net force in the vertical direction. In the horizontal direction, along the x-axis, we can add the pushing force and note that if the piano is not moving, there must be some other force pushing back against you. We can see that the resisting force of the piano is really the frictional force between the floor and the wheels of the piano and the friction in the wheel bearings. Since the piano has a constant speed of 0 and no direction, we can state Newton's first law as the sum of the forces is equal to the push force minus the force of the piano. This implies that the positive push force is equal to the negative pull force from the piano. Okay, let's wrap things up with a few review questions. Number 1, which of the following is the most accurate version of Newton's first law? The correct answer is C. Number 2, when you throw an object straight up, the object will slow down on its way up, stop for an instant, and then come back down with increasing speed in the opposite direction from its initial trajectory. Which of the following statements most accurately describes why this is the case? The correct answer is B. Number 3, which of the following reasons describes why an object would not move when you push it? The correct answer is D. Hi, and welcome to this video on Newton's second law of motion. In this video, we will look at Newton's second law, compare it with his first law, and look at a couple of simple, common applications. Let's get started. Newton's second law states the acceleration of an object is directly proportional to the net external force applied, and it is indirectly proportional to its mass. In other words, more force generates more acceleration for a given mass, but more mass means less acceleration from a given force. Newton's second law is generally written in the form of F equals ma, where F is the net external force causing a mass, m, to undergo an acceleration, a. Since m is a positive quantity, the acceleration vector points in the same direction as the net external force vector. Newton's second law can be considered an extension of the first law for the situation where the sum of the net external forces is non-zero. As with Newton's first law, the internal forces are not included, and it can only be applied in an inertial frame of reference. Let's take a look at both a one-dimensional and a two-dimensional example to illustrate some applications of Newton's second law. Let's say you have someone pushing a piano across a stage. In this example, we are interested in the moment when the person pushes the piano with just enough force to get it moving. Let's set up the situation in which the first law holds, that is, the situation of translational equilibrium. The forces in the y direction, as we have seen, are the force of gravity downward and the force of the floor pushing up. In the x direction, we have the push force of the person in the positive x direction and the force of the piano pushing back in the negative x direction. When the person pushes with enough force to overcome the frictional forces resisting motion, the piano goes from a zero velocity to a non-zero velocity, and any change in velocity constitutes an acceleration. Thus, during the time when the velocity is changing, the net external force causes an acceleration, and Newton's second law comes into play. For the sake of completion, let's toss some numbers into our equation to get an idea of the numerical value of the acceleration. Let's say the frictional force between the wheels and the floor is 10 newtons, and the total friction in the bearings of the wheels is 10 newtons. Using Newton's first law for the x direction, we can calculate the net frictional force to determine the minimal force the person must push with. Newton's first law tells us that any pushing force greater than 20 newtons will get the piano moving. While the person may not have made the numerical calculation we did, they intuitively knew they had to push with a force greater than the number we calculated. So let's say they push with a force of 30 newtons and calculate the acceleration using Newton's second law, assuming the piano has a mass of 200 kilograms. Restating Newton's second law as the sum of the external forces in the x direction is equal to the push force minus the force of the piano pushing back, substituting in the values we discussed and solving for the acceleration yields a value of 0.05 meters per second squared for the acceleration. We just used Newton's second law to calculate the acceleration of the piano in one direction given the external forces. Now that we know the acceleration, assuming it is constant based on the constant external forces applied, we could use the equations of motion with constant acceleration to calculate the time of travel and final velocity given the initial velocity and initial and final positions. In fact, given those three equations of motion for constant acceleration, you can find any three unknowns given the other parameters. Let's take a look at a 2D example using Newton's second law. In this example, we will also use a static inertial frame of reference fixed on the origin of our mass. Imagine you're involved in a three-way tug-of-war. Each person is 120 degrees from the other, and the x-axis is lined up with one of the warriors. Imagine, initially, each person pulled with equal force, and there is no motion, so Newton's first law applies. We can use vector math to show the force components from each person in the x and y directions, starting with the person on the right. We can see all of their force is directed in the x direction, so the force in the y direction is 0. The force from person 2 has components in the x and y directions, as shown. Similarly, the force from person 3 must be broken down into its x and y components, as shown. If we state Newton's laws for the three forces, we can see that Newton's first law holds. Let's say that the person aligned with the x-axis impulsively pulls with a force 1.3 times the force of the others. Using Newton's second law, we can calculate the acceleration of the center and the two people on the left. Let's assume that each person has the same mass of 50 kilograms and the rope has negligible mass. The mass of the system is then 150 kilograms. Now, let's say that F is equal to 100 newtons. Substituting those values into the force equation in the x direction and simplifying, we can calculate the acceleration. Intuitively, we know the direction of the acceleration is along the positive x-axis, and Newton's second law gives the quantitative value for the acceleration, which we calculated to be 0.2 meters per second squared. We just saw simple one-dimensional and two-dimensional applications of Newton's second law. When applying these principles to more complex examples, keep in mind that the concepts are the same, but the algebra may be a little more involved. Nonetheless, Newton's laws can be used to calculate the motion of all bodies in space, as long as they are moving in an inertial frame of reference. To wrap things up, let's go over a few review questions. Number 1, true or false? Unlike Newton's first law, Newton's second law is valid for bodies in motion in both inertial and non-inertial frames of reference. The correct answer is false. Both Newton's first and second laws are similar in that they account for motion in inertial reference frames. Number 2, true or false? Newton's second law is only valid for bodies with constant acceleration. The correct answer is false. Newton's second law can be used to find any acceleration. Number 3, calculate the acceleration of the body in the diagram given the parameters indicated, assuming the mass is not lifted from the ground. Also calculate the force from the floor. Here's the correct calculation of the acceleration of the body, assuming the mass is not lifted from the ground. And here is the correct calculation of the force from the floor.
Hi, and welcome to this overview of displacement, velocity, and acceleration. In this video, we're going to learn some fundamentals that help us describe the motion of bodies in space. To start, we'll define these three terms and see how they are related to each other. Then we'll look at some everyday situations and use some simple equations to make some reasonable evaluations. If we're going to talk about the motion of a body in space, we should take a minute to define this space. We live in a three-dimensional world with x, y, and z dimensions. But to simplify our description of motion for the moment, we're going to look at two-dimensional and one-dimensional motion first, so that we can define displacement, velocity, and acceleration. While the concepts are the same in one and two dimensions as they are in three dimensions, the algebra gets a little complicated and the arithmetic gets tedious, which is exactly why we're not going to deal with the math for three dimensions right now. Let's take a look at something moving along a straight line on a horizontal surface, since that's about as 1D as you can get. Distance is a reasonably intuitive idea. It's the total amount of space you go through to get from one point to another. It's important to be confident of this because it is crucial to differentiate distance from displacement. Displacement is the direct distance between the endpoint and the starting point of that spatial voyage, regardless of the path taken. Let's take a look at an example. Let's say that you let your cat outside to do whatever it is that cats do when they're out on their own. If we define a one-dimensional coordinate system where the door is at the position x equals 0, and the cat walks a distance of 3 units at a constant speed and then stops, you could say that the distance the cat traveled is 3 units. We could also say the displacement for that trip, the distance between the endpoint and the starting point, is 3 units. Now, like most cats, this cat is indecisive and decides to walk back and stand in the doorway. On the return trip, the cat walks a distance of 3 units, making the total distance of the cat's entire trip 6 units. However, according to the definition of displacement, which is the distance between the start and end points, the displacement for the cat's entire trip is 0. We can see this by looking at the equation displacement equals PF minus PI, where PF and PI are the final and initial positions. Notice that in the definition of displacement, the the direction of the motion is taken into account. Remember that physical properties that have magnitude and direction are called vectors. And this becomes important for our definitions of velocity and acceleration. Next, let's look at another example. Here we have a dog on a leash who has just been tied to a pole while its human makes a quick lunch stop. As you can see, the dog is constrained to move in a circle. It's easy to see that if the dog starts wherever it is right now and runs around in a complete circle, it has run the distance equivalent to the circumference of a circle, which is the distance of 2 pi times the radius. However, we can see that its displacement is 0 because the dog finishes where he starts, which means the difference between those 2 points is 0. Hopefully those 2 examples made clear the difference between distance and displacement, because that is necessary to define velocity and acceleration. Let's go back to our cat walking in a straight line along the x-axis. Let's say the cat walked from the door and went a displacement of delta x in a time delta t, where delta means the change in, as you might recall from learning the slope of a line. This change in displacement over time, t, is defined as the velocity and written as delta x over delta t. We can see that the cat walked 3 meters away, which took it 5 seconds to do. Notice the arrow over the velocity and displacement symbols, and recall there are 2 fundamental quantities in physics. One is a scalar, or something with magnitude only, and one is a vector, something with magnitude and direction. Velocity is a vector. There is a scalar counterpart to velocity that you already know as speed. Let's take a look at an example to make the difference between speed and velocity more clear. Going back to the dog on a leash tied to a pole, let's imagine that the dog ran at a constant speed of 1.5 meters per second for the entire journey around the pole. While we can say the speed may be constant, we can't say the velocity was constant because we see the dog's direction is constantly changing. In fact, the total velocity for the entire trip is equal to 0. Well, let's prove that visually. Let's break the circle up into 8 points, all opposite each other on the circumference of the circle. If you look at point 1, you can visualize that the dog's velocity at that instant is tangent to the circle. Of course, the rope pulls the dog inward in the next moment, so it doesn't follow the arrow in the diagram. If we look at point 5, opposite point 1, we can see that when the dog is there, it moves in the opposite direction as it does when it's at point 1, and that the directions cancel each other out. The same is true for the other pairs of points. So while the speed doesn't change, the directions do. When you map that out over the entire circle, all the directions have their opposites. You can see that they cancel out over the entire trip. The math is even easier. Looking at the definition of velocity as the displacement divided by the time, we can easily see that the difference between the start at P1 and the end, also at P1, is 0. So the total displacement for the trip is 0, and 0 divided by anything is 0. For the last of our definitions, acceleration, let's imagine that the velocity changes over time as represented by this graph, where the horizontal axis measures time and the vertical axis measures velocity. Suppose the change in velocity was constant. As the graph shows, the curve representing the change in velocity with respect to time is a straight line, and the slope of that line is the rate at which the velocity is changing. In general terms, the slope of a two-dimensional graph is the vertical change over the horizontal change. In this case, the y-axis is the velocity and the x-axis is the time. So the slope of the line is the change in the velocity divided by the change in time. This is the definition of acceleration. Acceleration is a vector, so we must make sure we incorporate the direction into our description of the motion. Let's use the graph to calculate the acceleration of a car moving at a constantly changing speed. If we write the definition of acceleration and then plug in the numbers, we can find that the average acceleration is equal to 3/4 meters per second squared. Notice the units of seconds squared in the denominator. This unit comes from the fact that v equals delta x over delta t. When we substitute that expression for velocity into the acceleration equation, we get time squared in the denominator. Sometimes it is said meters per second, which implies a change in the velocity of some meters per second every second. Let's take a quick look at a two-dimensional example of a football after being kicked off the ground. Suppose the football is kicked at an angle of 60 degrees with respect to the horizontal. Then sometime later, it's at position 2. We can see that the distance the football traveled is along the parabolic arc, but the displacement is just the hypotenuse of the right triangle that was just drawn. Clearly, the distance traveled and the displacement are not the same. We can also say that the football's direction is obviously changing, so it is not moving at a constant velocity, which means it's accelerating. Note that since gravity is pulling down on it, its vertical speed decreases as it moves upward. We know this because it eventually stops going up and starts to move back down. Now that we've defined displacement, velocity, and acceleration, let's test your knowledge. Number 1, what is the difference between distance and displacement? A, there is no difference. B, displacement is a scalar and distance is a vector. C, distance is a scalar and displacement is a vector. Or D, displacement doesn't account for the direction of the motion. The correct answer is C. The displacement is the difference between the start point and the end point. If they're the same, as we saw in one of our examples, then there must have been some change in direction. Number 2, when an object is launched into the air, does it accelerate? A, no, because no forces are acting on it once it is launched. B, no, because it never goes faster than the velocity it was launched at. C, yes, because even though its speed doesn't change, its direction does. Or D, yes, because its speed changes on the way up and down, and its direction is changing. Well, the correct answer is D. If you remember our football example from earlier, the ball slows down on the way up, which is enough to say it is accelerating, since either a change in the speed or direction constitutes an acceleration. In this example, the object is also changing direction. Number 3, the velocity of the Earth around the Sun after one complete orbit is A, approximately 30,000 kilometers per second, B, 0, C, the velocity is constantly changing according to Kepler's laws, or D, the same as the tangential velocity. The correct answer is B. As we saw with the dog moving in a circle, the directions of the velocity cancel out after one complete trip. Hi, and welcome to this video on kinetic and potential energy. Energy is a very important concept in physics that helps us describe how much work an object can do. While the word energy is often used in everyday language, the meaning in physics is very specific and may not exactly coincide with the meanings you are used to hearing. Today, we'll be looking at the different types of energy and how they affect the world around us every day. There are two main categories of energy: kinetic energy and potential energy. Kinetic energy applies to objects in motion. Potential energy is the stored energy of an object and depends on the object's position. Different types of energy may express energy values in different combinations of units, but the standard unit for energy is the joule. First, let's talk about kinetic energy. Since kinetic energy applies to moving objects, it is dependent on the object's velocity. The equation for kinetic energy is kinetic energy equals 1/2 times the mass times the velocity squared. Here, it is apparent that when v equals 0, the kinetic energy is also equal to 0. This makes sense because if the object is at rest, it won't have any kinetic energy. Also, kinetic energy is directly proportional to the mass of the object and the velocity squared. So the faster an object is moving and the heavier it is, the higher the kinetic energy will be. Kinetic energy is closely related to work. In physics, work is a measure of the energy it takes to move something a given distance. A force must act on the object in order to move it and cause work to be done. You must take all of the forces acting on the object into consideration when thinking about the total amount of work that was done on the object. So, the equation for work in terms of force and distance is the net work done on an object, W net, equals the net force that acted on the object, F net, times the distance over which the work was done, or D. However, it is sometimes more useful to think of work in terms of energy. The work-energy theorem states that work is equal to the change in the kinetic energy of an object. So, work is equal to the final value of the kinetic energy minus the initial value of the kinetic energy. It is also important to note that work can be either positive or negative. For example, if you were pushing a box across a table, the direction you're pushing the box would be considered positive direction. The friction between the box and the table is a force in the direction opposite to the motion, so the work being done by friction is negative. Basically, negative work makes it more difficult to get positive work done. Let's think about an example using the work-energy theorem. Imagine you're standing at the top of a building and you're holding a ball over the edge. While you are holding the ball over the edge, it is at rest. If you let it go, it will be in free fall until it reaches the ground and is at rest again. There are several questions we need to ask here. Are there any forces at work here? If so, what are they? Is work being done when you drop the ball? Does the amount of work change as the ball falls to the ground? To answer the first question, yes, there is a force at work here. The force that is acting here is gravity. Specifically, the force of gravity equals mass times the object's acceleration. Gravity is pulling the ball to the ground when you drop it, and the acceleration due to gravity, g, is making the ball go faster and faster as it gets closer to the ground. The positive direction here is downward in the direction of the movement. Since there is kinetic energy when the ball is moving, remember it has velocity, then work is being done on the ball by gravity. So what is the total amount of work being done here from when the ball is at rest to the time it hits the ground? Well, the velocity is 0 at both of those times. So the total work done is 0 after the ball hits the ground. This is because the normal force of the ground pushes upward on the ball and causes negative work to be done. The work from gravity is then canceled out at that point. However, if we look at the amount of work done when the ball is only halfway to the ground, we will have a non-zero value of kinetic energy, since the ball has a non-zero velocity. When we plug this into the work-energy theorem with 1/2 times the mass times the initial velocity squared equals 0, we will get a non-zero value for work. So, the value for the amount of work done will change depending on where the ball is on its way to the ground. So where does potential energy come in? Potential energy depends on an object's position. Unlike kinetic energy, an object can have a non-zero potential energy when it is at rest or when it is moving. The example where we are dropping the ball from the building involves a form of potential energy called gravitational potential energy. As you might imagine, the name comes from the fact that we are dealing with the gravitational force. The equation that we use for gravitational potential energy is gravitational potential energy equals mass times acceleration times the height of the object from the ground. So, In our previous example, the potential energy is at its highest when you are holding the ball at the top of the building because h is at its maximum value. The mass of the ball is not changing here, and g is always 9.8 meters per second squared near the surface of the Earth. So the potential energy is entirely dependent on how far away the ball is from the ground in this problem. When the ball hits the ground, it has no more potential energy. It's important to understand that during the fall from the top of the building to the ground, the ball has both kinetic and potential energy, and both are constantly changing. If you look again at the equation for gravitational potential energy, you might notice that the mg is actually the gravitational force acting on the object. And when we multiply that by the distance the object travels, we get the work done against gravity or by gravity, depending on the direction. So, if you're lifting the object up from the ground, you're doing work against gravity. And when the object is in free fall, gravity is doing the work. Work must be computed over some distance or some change in h. It doesn't make sense to ask what the work is at one point, say 3 meters above the ground. For work, you might ask something like, what is the work done when you lift the ball from a height of 2 meters to a height of 3 meters? So the work done by gravity is actually equal to the change of potential energy. Another type of potential energy is elastic potential energy. Elastic potential energy involves any type of object that can be compressed, stretched, or otherwise deformed in such a way that it wants to move back into an equilibrium position. Common examples are springs or rubber bands. Elastic materials all have a spring constant, K, that is dependent on the material and describes how elastic it is. The force of a compressed or stretched spring is described by Hooke's law, where K is the spring constant and delta X is the distance that the spring has been displaced. When the spring is in a stretched or compressed state, the potential energy associated with this state is potential energy of the spring equals 1/2 times K times delta X squared. So let's think about an example of a typical spring problem. Imagine a spring attached to a wall. When the spring is not compressed or stretched, the end of the spring rests at the spot we will call X equals 0. At this point, it has no stored energy. If you compress the spring by pushing it to the left, you've moved it by a distance delta X, and it now has stored or potential energy. The force of the spring is pressing in the opposite direction of the direction that you've compressed it. Conversely, if you stretch the spring by delta X, the force now points in the opposite direction. The elastic potential energy is the same here if delta X is the same. Now that we've learned all about kinetic energy, potential energy, and work, let's test it out with some problems. Let's say you have a bowling ball of mass m on a ramp that is height h from the ground. What is the potential energy when it is at rest at the top of the ramp and when it is at a height of 1/3 times h? Is it A, 0, 0, B, 0, 1/3 mgh, C, mgh, 1/3 mgh, or D, mgh, impossible to tell without knowing how long the ramp is? The correct answer is C. The bowling ball will have potential energy as long as it is on the ramp, so it won't be 0 until it reaches the ground. At the top, it is a height of h from the ground, and when it is at a height of 1/3 h, that is how far it is from the ground. The path it takes doesn't matter. In this same example, how much total work is done from the time the bowling ball is going a speed of v to the time that it hits the ground, assuming it stops when it hits the ground? Is it A, negative 1/2 mv squared, B, 1/2 mv squared, or C, 0? The correct answer is A. Here, the initial velocity equals v and the final velocity equals 0 because the bowling ball is stopped by the ground. Plugging these into the work energy theorem, we get negative 1/2 mv squared. The reason work is negative here is that we have to take into account the work done by the ground to stop the ball. This value is the net work of the ball-ground system. Imagine you have a spring with spring constant K hanging from the ceiling. In its equilibrium position, it is a height of 2 meters off of the ground. What is the elastic potential energy of the spring when you pull it down until it is only 1.5 meters off the ground? Is it A, 2K, B, 1/8 K, C, K, or D, 9/8 K? The correct answer is B. You've displaced the spring by 2 minus 1.5 equals 0.5, or 1/2 meters. Plugging this into potential energy of the spring equation, you get 1/8 K.
Hi, and welcome to this video on projectile motion. Today, we'll discuss what projectile motion is and break down some important concepts. Projectile motion occurs anytime an object is thrown or launched into the air and falls back to the ground. With physics, it's possible to predict things like where the object will land and the amount of time it will take for the object to reach the ground. Our ability to predict these values depends on the information we have about the scenario. When you begin a projectile motion problem, the first thing you'll have to do is think about the trajectory of the object. In other words, consider the direction the object is moving. Is all of the motion vertical, like an object falling to the ground? Or is the object launched or thrown at some angle? It helps to draw out the trajectory if it isn't already given to you. Even an approximation can be helpful in visualizing the situation. You'll want to determine your starting point, end point, and the path of travel. When we're working with projectile motion, we are dealing with vectors like velocity and acceleration, which we break up into the x and y components. This is because the motion in the x and y components are independent of each other. For example, at every point along the path of motion here, there is a velocity in the x direction and a velocity in the y direction. The x and y position changes along the path with x naught and y naught marking the starting point. For every projectile motion problem, we'll have a set of variables in each direction. Let's quickly go over what each of these variables are. X naught and y naught are the initial positions. X and y are the position vectors at the time you are solving for. V naught x and V naught y are the initial velocities in each direction. Vx and Vy are the ending velocities in each direction. And Ax and Ay are your accelerations in each direction. In addition to these variables, we have the time, t, which is a scalar quantity. So, there appears to be a lot to keep track of in these projectile motion problems. But before you give up and throw out your physics book, check out these simplifications. In any basic projectile motion problem you encounter, gravity will be the only force you have to worry about, since air resistance is usually negligible. This simplifies all of the acceleration variables. Gravity only acts in the y direction, so Ax will always equal 0. And assuming you're talking about the Earth, any acceleration in the y direction will always be g equals negative 9.8 meters per second squared. Note that it is negative since, by convention, we assign up to be the positive y direction and gravity always acts down. In most cases, you will set up the problem so that x naught equals 0, and in some cases where y naught equals 0 as well. We'll show you an example in a moment where y naught is not 0. If you have a problem where the object is launched straight up into the air and falls back down, or it is dropped from some height straight to the ground, then all of the motion is in the vertical direction and you won't need to worry about any of the horizontal parameters. So, how do you put all of these variables together to describe the motion of an object? You may have already been introduced to the kinematic equations. With this set of equations and the handy tips we discussed, you can solve any projectile motion problem. Don't worry, you won't have to use all of these equations for every problem. The trick to these problems is to be methodical. It helps to follow these steps. Read the problem and draw out a free body diagram if there isn't one given. Determine which variables you already know. Determine which variable you need to calculate. Let's look at an example of one of the most common kinds of projectile motion problems. Imagine you kick a ball off a cliff at a speed of 12 meters per second. The ball goes straight along the ground until it is over the cliff, which is 30 meters high. How long does it take for the ball to land? How far away does the ball land? We are told that the ball moves along the ground and goes straight off the cliff at 12 meters per second. This means that the initial velocity, v0, is only in the x direction and is 12 meters per second. So we have v0x equals 12 meters per second and v0y equals 0. We also know that y0 equals 30 meters and we'll set x0 to equal 0. As with most projectile motion problems, gravity is the only force we need to worry about. So the only acceleration is g equals negative 9.8 meters per second squared. Remember, this is only in the y direction and only after the ball is over the cliff. So ay equals negative 9.8 meters per second squared, which is 0 in the x direction. Now, what do we need to find? We are asked for the time, t. If we look back at our kinematic equations, we can figure out which equation to use to get the time it takes for the ball to hit the ground. It looks like we have everything but t for y equals y0 plus v0y times t plus 1/2 ayt squared. If we plug in v0 y equals 0, y0 equals 30 meters, and y equals 0, and ay equals negative 9.8 meters per second squared, negative because it is pulling the ball in the negative y direction, we get a simpler equation. 0 equals 30 plus 1/2 times negative 9.8 times t squared. First, subtract 30 from both sides of the equation. To get rid of the 1/2, just multiply both sides by 2. Then divide both sides by negative 9.8. Then just take the square root of both sides to get t equals approximately 2.5 seconds. This seems like a reasonable answer. It should only take a few seconds for a ball to fall 30 meters. Now we can find how far away the ball lands. Looking back at our equations, it makes sense to use the same equations, but for the x components this time. Remember, there is no acceleration in the x direction, so that is 0, eliminating the last term. But we said x0 equals 0 as well. So plugging in what we know, we get x equals 12 meters per second times 2.5 seconds equals 30 meters. The ball lands about 30 meters away from the cliff. Another type of projectile motion problem involves the object being shot upward into the air at an angle before falling back down. In this case, the initial velocity has both an x and y component, and you'll have to use simple trigonometry to determine v0x and v0y. Now that we've gone through a thorough overview of projectile motion, let's test your knowledge with a few practice problems. Number 1. Imagine throwing a rock straight up into the air at a vertical velocity of 4 meters per second, so that it goes up to a height of 2 meters before it falls back down into your hand. Is there any point in the rock's trajectory that its vertical velocity is 0? A. No, it gets faster and faster for the whole trajectory. B. Yes, halfway through its trajectory when it changes directions. C. No, it stays at 4 meters per second the entire time. The correct answer is B. The rock's velocity decreases from 4 meters per second to 0 meters per second when it reaches the height of 2 meters. Then it increases in speed again on the way down, but in the opposite direction. Number 2. If a cannon launches a cannonball into the air at an angle of 45 degrees from the ground at an initial velocity of 35 meters per second, the initial velocity will have both an x and y component, v0x and v0y. We know that the vertical velocity will change due to the acceleration due to gravity. Will the horizontal velocity change throughout the cannonball's trajectory? A. No, there are no forces in the horizontal direction, and that means there is no acceleration. B. Yes, if the vertical component changes, then the horizontal component must change too. Or C. No, but it might change if the angle were different. The correct answer is A. If there is no acceleration, that means the velocity must be constant. Gravity only acts in the vertical direction.
Magnetism is one area of physics that most people have first-hand experience with, since magnets are fairly common everyday objects. Today we'll be looking at different types of magnets and seeing just how magnetism works. So, what are magnets exactly? Simply put, magnets are materials that have a magnetic field. The magnetic field of a magnet is invisible, but it does have a visible effect when it repels or attracts other magnets in its presence. An example I'm sure you're familiar with is a refrigerator magnet. We know that both the magnet and the refrigerator door are magnetic and have a magnetic field because the magnet sticks to the refrigerator door. Every magnet has a north and south pole. The north pole of one magnet and the south pole of a different magnet will experience an attractive magnetic force when they are near each other, while the north to north and south to south poles experience a repulsive force when they are near each other. In order to describe magnetic fields, we draw magnetic field lines that come out of the north pole and reconnect to the magnet at the south pole. Magnetic field lines will never cross, and they will either loop back around to the opposite pole of the same magnet or connect to another nearby magnet. Technically, the field lines continue through the magnet, creating a closed loop. The denser these lines are, the stronger the magnetic field is in that spot. And as you might expect, if the magnetic field is strong, the magnetic force is strong as well. As a simple experiment, this concept can be visualized by sprinkling magnetic iron shavings around a magnet. The shavings will actually align themselves with the magnetic field. To make things even more interesting, you can add more magnets and see how the field lines change. It is important to note the relationship between magnetic fields and electric current. Moving charges create electric current. Anytime there is an electric current, there is also a magnetic field around it. The magnetic field disappears when the current is stopped. On a much smaller scale, magnets actually consist of many tiny magnets. The electrons naturally have their own magnetic fields because they are moving charges, even when bound in the orbitals around the atoms. For most materials, the electron orbitals are arranged such that all the tiny fields created by the electrons cancel each other out. This results in no magnetic properties. However, in some materials, the magnetic fields of the electrons are not all canceled out, which encourages neighboring atoms to line up with the field. If enough fields align, then all of those tiny magnetic fields add up to one big magnetic field, making the material magnetic. This state doesn't often occur naturally, but it can. In some materials, it is possible to align all of the tiny magnets and create a magnetic material. This occurs when the randomly oriented magnetic fields of electrons have the ability to change orientation. This property is referred to as ferromagnetism. Ferromagnetic materials are used to make artificial magnets like those on your refrigerator. Rare earth metals such as samarium and neodymium exhibit this kind of behavior. In order to magnetize a material, it must be submerged in a strong external magnetic field. The magnetic fields of the electrons in the material will then align themselves with the external field and remain that way. The ability of the ferromagnet to retain its magnetic ability depends on the material. Some artificial magnets are permanent, while others are only magnetic when they are exposed to another magnetic field. However, even permanent magnets will lose their imposed magnetic field at a certain high temperature, called the Curie temperature. Each type of magnetic material has a different Curie temperature. Magnets can also occur naturally, although naturally occurring magnets are generally weaker than artificial magnets. The strongest natural magnet on Earth is magnetite, an iron oxide also known as lodestone. A few other naturally occurring magnetic materials are hematite and pyrrhotite, which are both relatively weak magnets. Aside from minerals, the Earth itself actually has its own magnetic field, and although it is weak, it protects us by deflecting certain dangerous particles from our atmosphere. Although it is not intuitive, what we refer to as the North Pole is actually the South Pole of Earth's magnetic field, and the geographic south is the north end of the magnet. Now that we've learned all about magnets and how they work, let's test your knowledge with some review questions. Number 1. How would you draw the field lines coming out of the North Pole of magnet A if it was put right in the middle of the North Pole and South Pole of magnets B and C? A. Half of the lines coming from the magnet A would connect to the North Pole of magnet B, and the other half would connect to the South Pole of magnet C. B. The lines coming out of the North Pole of magnet A would all avoid the North Pole of magnet B as much as possible and connect with the South Pole of magnet C. C. The magnetic field lines in each magnet would still come out of the North Pole and only connect to its own South Pole, so all the 3 magnet lines would just cross each other. The correct answer is B. Field lines will always go from the North Pole to the closest South Pole and will never cross each other. Number 2. Given the arrangement of magnets, which of the following would you expect to happen if the magnets are fixed at their midpoints but freely able to rotate? A, B, C. The correct answer is B. The magnets will rotate as little as possible, but will turn toward opposing poles.
Hi, and welcome to this video about the resistance of electric currents. You plug in your cell phone to charge. You hear the roar of a car engine as it starts. You turn on a flashlight when the power goes out. These are a few examples of electric circuits. They bring electricity from a power source to an item that converts that power into something else. These circuits are made up of a power source, wires, and other components like switches and resistors. Think about the plumbing in a house. The pipes deliver water to places where you use the water, like your sink and shower. Similarly, electric circuits deliver electricity to items and places that can use that electricity, like a light bulb, refrigerator, or TV. Circuits deliver electricity using the flow of electrons through wires, and this flow is called an electrical current. Just like the water pipes create a flow of water molecules making up the water current, the circuit creates a flow of electrons making up the electric current. Current is measured in amperes, which is a unit of measure that tells us how many electrons are flowing through a point in 1 second. In order to cause the electric current to flow, a voltage is applied to the circuit. A voltage difference causes the electrons to flow, just like a change in water pressure causes the water to flow. We can also think of voltage like the pulsing of your heart to push blood through your body. Your heart pushes on your blood to create blood flow, just like voltage pushes on electrons to create current. Voltage is measured in volts, a unit of measure that tells us how good our power source is at pushing an electron. Just like water pipes have ways for the water to flow to be slowed, electric circuits also have ways for electric current to be slowed. This is called resistance. Resistance is like the diameter of the water pipe. A larger diameter water pipe has less resistance than a small diameter water pipe. Every material has an electrical resistance, and it is measured in ohms. We use the Greek letter omega to represent an ohm. This unit of measure tells us how easy it is for our electric current to move through the material. The wires in an electrical circuit have resistance, R. It is determined by the length of the wire, L, the resistivity of the wire, ρ, and the diameter of the wire, d.
through the equation R equals rho times L divided by D. In most circuits, we want the wires delivering the current to have as small a resistance as possible so the current can flow easily. However, high resistance can be useful in some situations. An incandescent bulb has a twisted piece of wire in it. When you flip the switch to turn on the light, the voltage pushes the current through the wire, which has a very high resistance, so it is difficult for the current to move through. The wire begins to heat up. Eventually, the wire is so hot, light is created. Light bulbs show us one way electricity can be used to change one form of energy to another. We are changing electrical energy into light and heat energy. Voltage V, current I, and resistance R are related through Ohm's law. V equals IR. From this relationship, we see that increasing resistance while keeping the current the same means the voltage must increase. It's like using your thumb to spray water from a hose. You have increased the resistance for the water to flow through the hose, so more pressure is needed to keep the same water current flowing. Resistors can be linked together in a long chain. This is called a series circuit. Linking resistors in this way means each resistor receives the exact same current. However, the voltage drops across each resistor are dependent on its resistance, R. Suppose we have 3 resistors in a row, R1, R2, and R3. We would like to replace these 3 resistors with only one resistor that has the same resistance as the original series. This is called an equivalent resistance. Since the current is the same in each resistor, the relationship is additive. R1 plus R2 plus R3 equals R equivalent. It's like connecting 2 garden hoses together. The hoses are in series and it takes more water pressure to push the water through the hoses. Similarly, it takes more voltage to push the current through many resistors in series. An example of resistors in series is a string of old Christmas lights. The light bulbs form a series of resistors. Each bulb has a resistance. If one bulb burns out, the entire string of lights does not light up. This is because the current has been cut off. To make the lights work again, you need to find the broken bulb and replace it, which can take a while. Newer strings of lights don't have this problem because the resistors are in parallel. This means they each have the same voltage across them, but different currents. If one bulb burns out, the rest of the bulbs still work because they still have current. The equivalent resistance of resistors in parallel is 1 divided by R equivalent equals 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3. This relationship follows from Ohm's law, which shows us how the current branches into different resistors. Let's wrap up with a review question. I want to string together 15 strings of Christmas lights. As I add more and more Christmas lights to my string, the lights get dimmer and dimmer. Why? A, I do not have enough Christmas spirit. B, adding more lights adds more resistance. Or C, adding more lights adds more voltage. The answer is B. The Christmas lights add more resistance through more bulbs and more electrical wire. The strings of lights lose more energy to the wire's resistance as it gets longer. Remember the definition of resistance? And the bulbs receive less voltage. Thanks for watching and happy studying.